The next thing we're going to talk about are some different forms of quadratic equations. And before we do that, I'd like to go back to different forms of linear equations. Notice right here I have a linear equation in standard form. It's a good line. I can type that right into Desmos and see how it looks when I graph it. But just looking at it, I cannot easily see what the slope is or what the y-intercept is. It's too hard to tell because it's not in right form. However, if I change it to slope-intercept form, I can easily see that the slope is -2, the y-intercept is 3. The same thing can be said for going from vertex form. Right here, this is a quadratic equation. I know it's quadratic because of the 2. It's in vertex form, and I can easily see that the vertex of this parabola would occur at 5, 6. Right here is the same parabola, but it's in standard form, and I cannot tell where the vertex is just looking at this form. So sometimes we want to change things from standard form into vertex form. And to do that, we're going to do something very similar to where we left off in our last video for step 12 when we were completing the square. So the first thing I want to do, I want to change this y to a 0. And now I'm going to go through this. I'm actually just going to move it to the other side of the equation even. I'm going to just erase things over here so that it doesn't get confusing. There we go. So now it looks a lot like the last problem we did when we had our quadratic and we were trying to complete the square. This cannot be rewritten as a binomial squared because it's not a perfect square trinomial. So the first thing I'm going to do is add 5 to both sides. I end up with x squared plus 6x equals 5. The next thing I'm going to do is take half of 6 and square it and add it to both sides, just like I did when I completed the square. 6 divided by 2 is 3. 3 squared is 9. Next, I'm going to rewrite the left side as x plus 3, the quantity squared. 5 plus 9 makes 14. At this point, I want to get it equal to 0 again. Remember, I'm not trying to solve this for x. I'm trying to get it into vertex form. So I'm going to subtract 14 on both sides. X plus 3, the quantity squared, minus 14 equals 0. And at this point, I can take out that 0 and replace it with y, just like I started with at the beginning of this problem. So change y to 0. Complete the square. Set your equation back to 0. And change 0 to y. Here we can easily see our vertex now. Our vertex is -3, -14. Finally, we're going to have some quadratic equations that are not going to be easy to factor. Nobody wants to figure out what 2.3 times 9.7 is and see if they can combine to -1.8. That's just dreadful. Additionally, doing this problem with completing the square, not very pleasant. When we are encountering problems that seem like all other methods are failing, we still have our quadratic formula. What you have here in your notes is just a way to remember how to write the quadratic formula. The negative boy, we write -b, couldn't decide is plus or minus. Whether or not to go to the radical party, we draw a big radical symbol. The boy was square and was turned down, so negative, 4 awesome chicks, 4 AC. And the party was all over by 2 a.m. There's lots of ways to remember the quadratic formula. That's just one way. You can go on YouTube and find many, many other ways as well. So let's try, we're going to start with number 2 here. In order to apply the quadratic formula, we needed to equal 0. So I'm going to add 7x to both sides. 4x squared and 7x, take away 9, equals negative 4. Then I'm going to add 4 to both sides. That leaves me with 0 on the right. 4x squared plus 7x. Here I have some like terms, which makes negative 5. The a in our quadratic formula is the coefficient of the quadratic term. The b is the coefficient of the linear term. It's right next to x. And c is the constant. So I encourage you to write these out. A, B, C. It's very important to know which one is which. A is 4, B is 7, C is negative 5. Now we're ready to take these values and put them right into our quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now I encourage you to take out the variables and leave parentheses behind. Because when you substitute, when you have negative numbers going in, you really need to be careful with those negative signs. So as you can see here, negative b, if I put a 7 in there, it's negative 7. B squared minus 4 times a times c all over 2a. At this point, we just need to do some simplification. One of the easiest things is to do 2 times 4, which is just 8. I'm not going to write negative parentheses 7. I'm just going to write negative 7. Let's simplify inside of our radical. 7 squared makes 49. Negative 4 times 4 is negative 16. Times negative 5 would be a positive 80. Continuing to simplify, we have negative 7 plus or minus 49 plus 80 is 129. Now, I can't take the square root of 129, but we should check to see if we can break it down into some divisible pieces. So, is there a perfect square that divides into 129? If you're not sure right off the top of your head, I do know that I could divide it by 3, and I'd be left with 43. 43, however, is a prime number. There's nothing else that I could divide that by. So 129 actually cannot be simplified any further, which means that is our answer. Now, you can type this on a calculator. I'm going to do that right now. I'm holding a calculator right here with me, and I'm going to type it into the calculator. And divide by 8. My first answer is 0.545 rounded to the nearest thousand. And when I do the other one where I'm subtracting radical 129, I end up with negative 2.295. Sometimes the problem will indicate that you can round to the nearest thousand. If that's the case, these are acceptable answers. Otherwise, just keep it in most simplified form with the radical. This answer right here is actually more accurate because there has not been any rounding. The last thing I want to talk with you about is the discriminant. Believe it or not, you actually already know what the discriminant is. When we look at the quadratic formula, the discriminant is simply all of the stuff under the radical. It's a real technical term there. But the discriminant is b squared minus 4 times a times c. And the reason this is helpful, you can just calculate b squared minus 4 times a times c for a particular problem. And without finding the solutions, without solving by factoring or the quadratic formula or completing the square or graphing, you know how many solutions this particular graph would have. Remember, a number can be one of three things. It can be negative, it can be 0, or it can be positive. If a number is negative, imagine what a negative number under a radical looks like. I'm going to just pick a number, negative 7. Radical negative 7, you'll remember from step 11, is an imaginary number. So if the number under the radical is negative, we end up with two complex roots, just like this, if the number under the radical is negative. If the number under the radical is 0, remember how the quadratic formula goes, that means that we are adding nothing to b over 2a, and we're left with one rational root. The third option is that the number under the radical is positive. If that happens, we're going to end up with two real roots. But we have to explore further. Sometimes the number under the radical is going to be a perfect square, like radical 81. If the number under the radical is a perfect square, then we end up with two real rational roots. The way you can remember that, radical 81 is a rational number. It's just 9. Other times the number under the radical, like maybe 83, this is an irrational number. So we would end up with two real irrational roots. This concept summary just summarizes everything that we've practiced so far. We practiced graphing in step 10. We started out our first video for step 12 by factoring. We then used the square root property and completing the square. And then finally in today's video we practiced other methods to use, like the quadratic formula when all the other methods are failing us.